Okay, so if you did the in-class problem, you'll see that if we have a proportional integral and a derivative controller, we can change our transfer function. We know that our transfer function will determine how our system will behave with various inputs. So if we can see how it will change within a given reference point, we can predict how the system will work. But now we want to switch it around. We have this idea of how controllers work within a system, how it works within reference control, but now we want to design what is going on exactly. And the way we're going to use this is a method called the root locus diagram. And what a root locus diagram allows us to do is allows us to visualize the effect of changing a given parameter, maybe it's our p-value, I, d, some combination, on our pole locations. So if we think about that, that control loop, so you guys probably have this drawn, so you can rate those terms, but if we just want to take one proportional controller, so the root locus is built based off of looking at one parameter at a time, and it's formed based on the proportional controller. So we have some sort of reference, we have our open loop system, and this open loop system is one in which we do not have a feedback loop added. And we want to see how adding a proportional control can change the poles of our closed loop situation. So this loop, and let's draw it again in purple, is what we are closing. So we're going to refer to this as our closed loop poles, would be the transfer function of the full system. And the open loop is our starting transfer function before we close that loop. So what I want you to do is, you are champions of block diagrams. I've started grading the exams. People seem to be doing a pretty good job. So what is the transfer function of our closed loop system? And if we call this y, let's say y of s over r of s. So you can go ahead, press pause if you'd like. If you don't, then we'll not keep you in suspense long. It's going to be kgo of s times 1 plus kgo of s. And if we look at the denominator and set it equal to 0, we look at our characteristic equation. I'm hearing commentary about me teaching while in the background, which is always fun. So my daughter's asking about me. We have our characteristic equation of 1 plus kgo of s, and we set that equal to 0. So we set our denominator equal to 0, and the solutions of that are the poles of our function. So, you guys mentioned you can't ask me questions. I can't ask you questions during the lecture, and it's fun to have you to play off of. But this characteristic equation is going to be the rules that govern the root locus. So let's go ahead and see how that works. Okay, so I assume you're taking notes at the same time. You can just look on top of your page. We have that characteristic equation, 1 plus kgo of s is equal to 0, and this comes from that feedback loop. And these are going to be the rules that govern our root locus. So if we have a proportional k, which means k can be any real number, then we want to see the effects as we change k from 0 to infinity. But we know that there's going to be some things that will always be the same if we have k as a real number. So we can set kgo of s equal to -1. So we just take that characteristic equation, pull that 1 to the other side, so we have kgo of s is equal to -1. So the magnitude of kgo of s will be equal to 1. And the angle of kgo of s will be equal to 180, because 180 degrees, because if we visualize a -1, so if we have a point at -1, we would say that that is on our real imaginary plane, that would be 180 degrees from our starting angle. But it could be 180 degrees. It could also be, if we want to go around a few times, 180 times any number of circles. So we're going to say 2n plus 1 to represent the fact that as long as if we end up having an angle that points towards -1, we're okay to go. So we can have any number of circles that we'd like. Which seems a little bit strange. When we get into angle criterion, it'll make a little bit more sense. So let's go ahead and see an example with a real system so this can start to have some context. Okay, so we're going to have an example with GO of S is equal to 1 over S times S plus 2. So this is our open loop system. So it represents, if we just had an input system, we could see some sort of, if we just had our input system, we would have an input, and this would be the relationship between input and output. But we want to put this into a feedback controller, in which case our characteristic equation with a feedback loop, so once we've closed the system, would be 1 plus k GO of S is equal to 0, which for this example would be 1 plus k over S plus 2 is equal to 0. Now, what I want to do is I'm going to write down a couple different values of k, and what I'd like you to do is to come up with some values for where the poles would be. So I will write the values of k. So we'll have 0, 3/4, 1, 2, and 10. And now is a good point for you to press pause, and after, you're going to figure out where the poles are. So if k was 0, then our characteristic equation would stay the same, because we can go take this S plus 2 point and say that we have S plus 2 plus k is equal to 0. So our poles would match the poles of our open loop system, which would be 0 and -2. So I'm going to go ahead, let you press pause, and I'm going to do the same to change the colors of this. Okay, so I realize that I want to use color because we're not stuck with green chalkboards, so we can be a little bit more creative. And we started off with our open loop poles at 0 and -2. And if we go ahead and we look at what happens when k is 3/4, we now have S plus 2 plus 3 over 4 is equal to 0, which gives us true values at negative 0.5 and negative 1.5. So because we have s squared plus 2s plus k is equal to 0, and so if we do the quadratic equation, when k is equal to 3/4, those are our answers. So we'll do that again for 1, 2, and 10. And so again, you can pause and see if you can figure this out as you go through in your notes. Okay, so if you've done this on your own, we can see that we have poles at -1 repeating. So we have 2 poles at -1 repeating. And if k becomes 2, then we have a pole at -1 plus or minus 2i. And if we are at k is equal to 10, we have poles at -1 plus or minus 3i. And so there's one way down there. When you're designing a system, you don't want to manually calculate out each set of poles for each k value. It'd be nice to be able to predict what's going on. And what we're going to be doing with our root locus is we're going to be able to trace a path. So if our system starts at starting with k equals 0, as we increase the k, we're going to see that our poles can change in values where they meet up in the middle, and then extend, so they start with an overdamped system and then become an underdamped system as we increase K. And we're going to work more with this as time goes on. So my next lecture is going to talk about how that magnitude and angle work out in trying to develop the rules of a root locus system.